guys any questions on their homework?
When you're in that process and they give you the, that, pick your number where you wanna go, where it says, 0.35, 0.25, point whatever five, or the 1 point whatever five, like, they want exactly 95%. Your table on the Z-score says it is 1.625. But when you try to plug that in to actually do an exact 95%, you don't get the correct answer. You go back to the table and it's either one before or one after. So how do we figure out which way we're supposed to balance that to split that hair?
Okay, so you mean given a left area, find the Z-score? Okay, so just pick the left area that's closest to the one that you're trying to find. And if there are two that are exactly the same distance, I won't do that to you. So just pick
No,
one.
I understand you're not, right? Based on the table, it's like you get that point whatever five, so it's directly in between two. Are we supposed to average it out? Are we supposed to grab, depending on which direction they wanna go, is the one we're supposed to go with?
No, just select the one that is the closest absolute distance.
Okay.
And that'll be true for using tables in general in this class. So this, turns out it won't be the only table we use in the class. For other tables, if you need to find a certain value, then if that value is not there exactly in the table, you pick the closest one. Alright, good question. Anybody else? So all weekend apparently the homework was down. The server was down all weekend, so I'll give you an extension accordingly, depending on how long it'll be down for. And at the very least, the extension's till tomorrow, but longer if necessary. So anybody tried to access the homework recently?
I did right before we came to class, my math lab's back up.
Okay, good. So yeah, they got their act together.
I accessed it by clicking the orange button, and when I did, it brought up like a user agreement for Pearson. And then I clicked agree, and then it said your instructor has to like unlock the course, so that was weird on my
So that was
end.
probably when it was down.
Okay, so I checked that this morning
Okay.
around 11:30, I don't know.
So those guys who got it working, was it after 11:30? Yes.
Okay,
That's probably.
okay.
Okay, good. Any other questions? Okay, so let's continue. So last time we were talking about times in which we use bell curves. So in this class, there's gonna be three situations. The first one is the most straightforward and the easiest, and we've already talked about that situation, which is it's given to you that a certain variable is distributed as a bell curve or normally distributed. So it's given, so oftentimes you're just flat out told this variable is normally distributed, like the weight variable or the IQ score variable is normally distributed. But in real life, if it's not just told to you, it can be easily observed. So based on the data points you observe, construct a histogram. So take the values and see how often each one occurs, construct a histogram, and if you see that it's roughly bell-shaped, then you can make a good assumption that the variable for the population is also normally distributed. So it's either given or observed that the variable is normally distributed. And oftentimes in this situation, the mean and the standard deviation will also be given or be able to be observed by you. So mean, standard deviation given. So an example of that situation is, so the example, i.e., so you're told that weights of men are normally distributed. So with mean equals 180, standard deviation is 20 pounds. And then we want to find probability that a man's weight is more than 200 pounds, for example. So in this case, you're told that weights of men are normally distributed. We can visualize that by looking at the graph of this distribution. So the variable here will be man's weight. And you're told that weights of men, or each man's weight, is normally distributed. So you can go ahead and draw out the normal distribution or bell curve. And it's given to you that the mean is 180 and the standard deviation is 20. And you want to find the probability that this variable is greater than this number. So you locate the number on the distribution for the variable. And we said that there's an equivalence between probability and area. So since we're trying to find the probability of the variable being greater than, that's equivalent to an area of being to the right under the distribution. So in this case, this probability just reduces down to this issue of finding the area to the right of this value of the bell curve. So then,
One standard deviation would be 68%, so your probability is 32%.
okay, so let's write it. So remember we said that the general steps that work for all cases, anytime you're trying to find the probability between two values or relative to one value, is to find the z-score. So this z-score will be, the z-score of this data point is the number of standard deviations. That data point is away from the mean. So that data point is 200 minus the mean, which is 180, and then divide by number of pounds at each standard deviation. So you're gonna get 20 over 20, because 1. So this tells you the z-score is 1. In other words, it's 1 standard deviation away from the mean. So then what we do is, we said that there was a relationship between z-scores and area to the left of the z-score, laid out through a table for you. So in this case, we're looking for a z-score of 1, and then we're gonna look for the total area to the left of that. So what does the table give us?
0.8413.
0.8413. That's the left area. Recall in this case, we want the area to the right of that z-score, not the area to the left. So how do we get the right area?
Subtract that from 1.
Okay, subtract from 1 because the total area under the probability distribution will be 1. So 0.1587. So that's the answer to this question, which is the probability that a man's weighs more than 200 pounds will be 0.1587 or 15.87% of the time. Any questions so far? So let's review of the first situation. We use bell curves. This is the most straightforward. It's basically given to you, and you just straightforwardly use the tools, calculate the z-score, and use a table. So the second situation, we use bell curves. Last time we talked about that was the central limit theorem. So central limit theorem says that if you have a variable here that you're looking at the distribution for, and that variable isn't individual values, like the individual value of the weight of each man, but representing sample mean. So if you have a particular sample of whatever size, like size 50 people or size 100 people, if you take the average of that sample, and then you look at how often that value occurs for the entire values of all sample means, then the shape of this distribution will end up being a bell curve. And this is what the central limit theorem says, is that the distribution of sample means will end up being a bell curve, and the mean of this bell curve will equal the original population mean of individual values and the standard deviation will equal the population standard deviation of individual values, but divided by the square root of the sample size. So this is what the central limit theorem says. So in context, we said that, let's say the original situation was that it's given D that weights of men are normally distributed. But let's say that instead of selecting one individual man and saying whether his weight is more than 200 pounds, let's say we select a sampler. And so, select sample of, let's say, 100 men. And now we want to know the probability that the mean of that sample I'll say the mean weight of that sample is more than 200 pounds. So again, this looks very similar to the previous question. The previous question is the probability that one man's weight is more than 200 pounds. This question is the probability of the mean weight of that sample of 100 men weighing more than 200 pounds. So they look similar, but they're conceptually very different, right? So again, one is the probability that one value is more than 200 pounds. The other is the probability that the average of 100 values is more than 200 pounds. And so this variable ends up basically reducing down to the notion of a sample mean. So the mean value of a sample is a sample mean. So we said that the central limit theorem says precisely this, which is the distribution of sample means will end up being a bell curve with this mean and this standard deviation. Make sure that the assumptions that we talked about are met. So the assumptions are one of two things has to be true. You guys remember?
The sample size has to be over 30, or there already has to be a normal distribution.
Okay, excellent. So either the sample size n has to be at least 30, or the original population of individual values is already normally distributed. So either the sample size is at least 30, or the original distribution of individual values is already normally distributed. So that's the fine print that has to be true for you to be able to assert that we're going to have a bell curve if we have a distribution of sample means. So in this case, we're trying to find the probability of this variable, which represents a sample mean, is greater than 200. So using the central limit theorem, we know that the distribution of sample means is a bell curve, that we draw out. And then we look at where this number 200 is on that distribution. And since we're trying to find the probability of being greater than, that's gonna correspond to an area to the right under the bell curve. So the hardest part here is to recognize that we're dealing with a central limit theorem because we're dealing with a probability that involves a variable representing a sample mean. And once we recognize that, the distribution of sample means will end up being a bell curve by the central limit. So now that we have a bell curve problem with its own mean and standard deviation, now we're back to the previous idea. So basically, to find this area for this bell curve, find the z-score using the correct mean and standard deviation, and then look it up in the chart. So same as before. So in this case, the z-score will be 200 again, minus the 180, divide by,
Square root of 100, so 10.
yeah, so then it'll be divided by population standard deviation, which is given at, over here, at 20. So divided by 20, and then this, the new standard deviation is the old standard deviation divided by the square root of n. So it would be the square root of 100 here. So again, using the z-score formula, this is the data point, this is the mean, and this is the new standard deviation in the problem. Okay, so if you calculate that, you'll get 20 divided by 2, and that'll give us 10. So in this case, the z-score is 10, that means it's 10 standard deviations away from the mean. So if you start at the center of the mean, you have to move 10 standard deviations before you get to this data point on the curve. And we want to find the area to the right of that data point on the curve. So it's going to be something very small because that z-score is all the way to the right. And the area right to that is going to be a very small quantity left over. So this original drawing is not to scale based on the z-score we ended up getting. So if we redraw that, so that z-score is going to be all the way out here. And we want the area to the right of that, under the bell curve. So it's going to be this tiny area that's left over here on the right. So last time when we did this, we looked it up in the chart and saw that using the chart, it maxes out at a z-score of 3.5. Because at a z-score of 3.5, which let's say is here, the z-score table tells us that the area to the left is 99.99%. Yeah, so if the z-score had been 3.5, then the left area would have been 99.99%, and the right area would have been 0.01%, which is 3 zeros and 1, as a decimal. But our z-score isn't 3.5, our z-score is 10, which is to the right of that, which means our right area will be even smaller than the right area of 0.01%. And so that was the conclusion we made last time about this problem. So the point is that this probability we're looking for, that the average weight in a sample of 100 people will be more than 200 pounds, is virtually zero. It's a probability of even less than 0.01%. And we contrast that with the probability of one man weigh more than 200 pounds. And we said that that was 15.87%. And that was not a negligible number compared to the other two. Questions?
So if we have an answer like that in my math lab, would we express that as 0 plus or less
Yeah.
than?
It'll probably ask you to round to a certain number of decimal places, like 3 places. So in that case, if you're just rounding to 3 places, it'll just be 0.0.
Okay.
The opposite is also true because it'll make you put in one for that difference for things.
Right, so if it's 0.9999 and you have to round, and it'll end up being 1, yeah.
Yeah, so for example one, when you got 0.8413, I just
Mhm.
wanna ask how you got that really quick so I can clarify.
Oh, sure. Yeah, so once you get the z-score, in example 1, the z-score we got was 1.0. And then next step is to look up in the z-score table.
Okay, that's what I
And
thought.
yeah, the z-score table, if you look up z-score of 1, you'll get the left area as 0.8417. This is from the table.
0.8413.
Oh, 1.3, thanks. Okay, so this is review. Any questions? So these are the 2 times we talked about so far where we use bell curves. Let's talk about the third case. So the third case will be titled a normal approximation. To a binomial probability distribution. Okay, so let me build up to this. Let me put it into context with an example. So let's say the example is let's say that you flip a fair coin 100 times. And let's say that the question is, you want to find the probability that the number of heads you observe out of 100 flips is exactly 55. So find exactly 55 heads out of 100 flips. So this should actually be the review. Anybody happen to remember how to approach this?
Every one of them is independent, correct? So then it's gonna be, you have a 50-50 chance, so, 1/2 for each one, and then it's this, and this, and this, so it ends up being multiplied 55 times, so it'll be 1/2 to the 55th power.
Okay. Anything else?
And trying to remember, do you subtract that from the probability of 1?
Okay, very good, so you're on a great, on a great track. So, you want 55 heads, and like you said, that means you want the first to be heads and the second and the third, so probably with and is multiplication, so you multiply all these probability of heads together. But because you want this number of heads out of 100 flips, that implies that you are gonna get how many tails?
45.
Yeah, 45. So basically, we're gonna do exactly the same thing for the number of tails that you want. So for 45 tails, you now multiply the probability of tails for each flip, which is also 1/2. Multiply that 45 times. But what's missing?
X, 100, what is it?
Choose.
Choose,
Okay, good, good.
55,
Okay, good. So why is that missing?
it's part of the formula.
Yeah, part of the formula. Why is it part of the formula?
We need to know the number of possible, we need to know the number of possible ways you can have heads or tails.
Yeah. So this is just one probability for one sequence of 55 heads and 45 tails, but it turns out that there's lots of sequences where you get 55 heads and 45 tails. So now you have to add the number of those sequences together. And the number of times you add it means that you multiply by the number of times. So now you have to multiply by the number of such sequences of 55 heads and 45 tails. So the ways that you can pick 55 heads from 100 flips is 100 choose 45, or 50. So very good. So these three components are necessary to the final answer, and this constitutes the formula, the binomial probability formula. Okay, so go ahead and punch this in. You have the calculator. See what you get. .04847. Great. So this represents the exact answer to this question of the probability of getting 55 heads out of 100 flips. And the remaining flips are 45 tails. So this is the exact answer. But let's try to see if we can approach it another way. So let's think about what this distribution would look like. So if I had this variable that represented the number of heads observed out of 100 flips of a fair coin, remember in a distribution we can represent that with a table of two columns. One is the variable x of interest, and the other is the probability of each x, taking on each of its values. So if you look at the first column, what are all the possible values for that variable, representing the number of heads you could observe out of 100 flips?
0 and 1.
0 through 100. Right? Okay. So 0, 1, 2, 3, all the way up to 0. And then how do you find the probability of each variable?
We use the binomial probability distribution.
Yeah, very good. The probability of each of these x values would be the binomial probability formula, because we're dealing with, for each of these, probability of a number of successes out of another number of trials. So each of these probabilities is the probability of this particular number of successes out of 100 flips. So that structure is a binomial probability, and we would just put in, each of these would be the binomial probability formula. So if we have a probability distribution where all the probabilities are binomial, then we call that specifically what kind of probability distribution? So by itself, we have a table of two columns, x and p of x. This is an ordinary probability distribution. And we talked about how you can find the mean and the probability of any ordinary probability distribution. But in this case, you have a special probability distribution. It's not just ordinary. So what kind of probability distribution did we talk about? Okay, good thing we're reviewing. So recall, if all these probabilities end up being binomial probabilities, where you can use this binomial probability formula to get these probabilities, then this whole distribution is a binomial probability distribution. So we're combining the ideas of a probability distribution and binomial probabilities to get a binomial probability distribution. So what was special about a binomial probability distribution in terms of how you find the mean and how you find the standard deviation? Yeah.
You can use, like, multiply, n trials by the probability to get the mean, and then for the standard deviation, you would use NPQ.
Okay, very good. So there's special shortcut formulas in finding the mean and the standard deviation if you have this special case. So the mean ends up being simply n times p, and the standard deviation simply is the square root of npq. So in this case, what's the mean number of heads that you should expect to observe if you flip a fair coin 100 times?
50.
50, good. And the way that we get that 50 mathematically is n, which is 100 flips, times p, which is the probability of heads per flip for a fair coin, is 0.5. So the mean is 100 times 0.5, which is 50. And this is mathematical, but of course, you can get this answer by common sense. If you have a fair coin and you flip it 100 times, even if it's perfectly fair, you're not going to get 50 flips every time, 50 heads every time you flip it 100 times. But in the long run, it'll average out to 50 heads for the 100 flips, if you have a fair coin. So this is the mean. The standard deviation will be the square root of 100 times p for a fair coin is 0.5. Q, remember, is 1 minus p, where if p is the probability of success per flip, q is the probability of non-success per flip. So non-success in this case is tails. So q is 1 minus p, or the probability of tails, which is also 0.5. So if you work this out, this will equal 5. So this is square root of 25. So now that we have the mean and the standard deviation, this is one way that we could represent this probability distribution as a table of two columns. Another way that we could represent a probability distribution is a graph with two axes. So let's look at the graph. So Again, the x-axis here, the variable involved is the number of heads observed out of 100 flips of a fair coin. So, again, if you flip this fair coin 100 times, what is the number of heads you should expect to observe with the most likelihood?
50.
Yeah, 50. So at 50 here, we're gonna have a bar with a certain height, where that height represents the probability of observing that many heads out of 100 flips. So let's just call this the probability of x, where x is defined as the number of heads observed out of 100 flips. So if you have a fair coin that you flip 100 times, you should expect to observe 50 heads with the most likelihood, where the height of this bar is the highest relative to all the other values. Now, just because the coin is fair, and assuming that it's perfectly fair, should you expect to observe 50 heads every time you flip it 100 times? No. So you very well could observe 51 heads for a fair coin if you flip it 100 times, but it'll be less likelihood. The probability will be lower. So that'll be indicated where the height of this bar is lower. And same thing, as you move away from 50, further and further, the probability will get less and less that you actually observe that number of heads out of 100 flips for a fair coin. And same thing for the other direction. Okay, so this is what the distribution looks like visualized. And again, we said that this is a binomial probability distribution. And this is what that binomial probability distribution looks like. So you notice that it peaks somewhere in the middle, and then it looks like it's symmetric on both sides. And if you were to stand far away and kind of squint a little bit, then this overall shape looks like what?
A bell curve.
Yeah, it looks like a bell curve. So if you were to approximate this, the general shape of it would end up being a bell curve. So you notice that you have two different distributions here. They're not one and the same. The original black distribution is the original binomial probability distribution. And the one in green is what we call the normal approximation to the binomial probability distribution. So the green is the normal approximation to the binomial Okay, so you have these two distributions. One is the original distribution, the other is just an approximation on the general shape. And so notice that for each of these distributions, we can find the probability for each distribution, but in different ways. So for example, if we were just looking at the original binomial distribution, and by the way, the original binomial probability distribution, you notice, is it discrete or continuous? The original black distribution.
Discrete,
Yeah, discrete one.
because there's only two outcomes.
Yeah, not only that,
It has a finite amount that's being used for the numbering scale.
yeah, so you notice that all the values that are possible that could have representation for those values, there's only a limited set of values that could have representation. So in other words, you notice the distribution has a whole bunch of gaps in it. So there's these vertical bars with gaps. And the gaps correspond to where the values don't have any representation. So for example, between, if this is 52 and this is 53, there's a huge gap between 52 and 53, and that's because there can be no representation between 52 and 53, because this represents the number of heads that you could observe out of 100 flips. And you can't observe 52.6 heads out of 100 flips. So that's why between any sets of whole numbers here, you have these gaps that represent zero probabilities. That represents no representation. So in a discrete distribution, there are huge number of values in the spectrum that have no representation. And we call that a discrete distribution. Versus a continuous distribution, the bell curve, where all values in this range are possible, have representation. And so, if we're looking at just the original binomial distribution with the gaps, then how would you find probabilities? So if I were to ask, what's the probability of either 54 or 55 heads, or 56 heads, how would I find the probability of this situation if I were to use the original distribution in black?
Figure out your largest one, figure out your smallest one, subtract your answers from each other, and report the area for the two that you're doing. 'Cause you're
Okay.
basically reporting the area between those scores to give the answer.
Okay, so what you're describing in order to find the area is if you're assuming a distribution that is continuous. So this green distribution is continuous, and you would find probabilities using areas. But if we didn't have the green distribution, if we had the original black distribution only, then how would we find probabilities? So then, the probability of a discrete distribution is you would look at the height of each of the bars and then add up the relevant heights. So for example, in this case, if we're trying to find the probability of 54 heads, you look at 54 here, look at what its height is. It's gonna have this height corresponding to that probability. We know what that number is, and then do the same thing to these other number of heads. Look at 55 and look at 56. You're gonna get these three heights corresponding to the three numbers that you add together, and that'll correspond to the final probability. So in a discrete distribution, to find probabilities, you add up the appropriate heights. But if we were to convert this to a situation where we're fitting a continuous distribution like a bell curve onto it instead, now we're gonna find probabilities differently. We're gonna find probabilities using areas instead. So now, if we want, in the previous question, if we want the probability of exactly 55 heads, in the original problem, we're just finding the height of the bar at 55. And that corresponds to finding this exact number using the formula. We found that exact number, so the height of this bar at 55 is 0.04847. So this is at 55 heads. And that's finding the probability using only the black distribution that is discrete. But if we now use the other distribution, which is the approximation, which is the green bell curve, then we said to find areas using a continuous distribution, like a bell curve, then we would probability we find using areas instead. So, but we said that if you have a bell curve and you're finding the probability of exactly this data point under the bell curve, then mathematically, by definition, that probability ends up being what? The probability of a single point under a continuous distribution.
0.
0, very good. Because finding probability using a continuous distribution is finding area, and the area of a single point under a curve is 0, mathematically. So we know that the answer is not 0. The answer is actually the height of whatever this bar is, and it should be 0.0487. So how do we find the area of a point using an area? So what we'll need to do is give each point a region that we can find the area for. So based on how we round numbers in real life, we're going to arbitrarily adopt a convention of each data point has a region of 0.5 in either direction. So this data point of 55, we're going to now assign an area around it, so that we can find the area of that region to represent the probability of that point using this continuous distribution, this bell curve. So this data point of 55 has an area of 0.5 in either direction. So 55 minus 0.5 is 54.5, and 55 plus 0.5 is 55.5. So now we're going to approach the same problem of finding the probability of exactly 55 heads. The first time, we essentially found the height of the bar at 55 using this formula. The new approach is we're going to fit a bell curve and find the area around 55 of 0.5 in either direction. So we're going to find the area under the bell curve between 54.5 and 55.5. And we're going to get an area, we're going to get an answer that is very close, if not exact, to this answer. So let's try that. So the second approach is this is the normal approximation. This is this case. So now we have a bell curve problem where we're trying to find the probability between these two numbers, 54.5 and 55.5, with this mean and this standard deviation for the bell curve. The mean is 50, the standard deviation is 5. And we got those values because we realized this is a binomial probability distribution, and we were able to find the mean and standard deviation easily. So this is back to the regular z-score problem, regular bell curve problem. So find the z-score of so we're going to find two z-scores. One is 55.5 and one is 54.5. So for 55.5, we're going to take the data point 55.5, subtract the mean, and the mean is 50, good. And then divide by the standard deviation, and the standard deviation is 5. Good. So if you calculate that, we'll get 55.5 minus 50 is 5.5 divided by 5, which is 1.1. And then while we're calculating z-scores, let's calculate the z-score of the other boundary, 54.5. So that will be 54.5 minus 50 divided by 5. So that will be 4.5 divided by 5, which is 0.9. So now that we have the z-scores, we're ready to look them up in the chart to find the areas to the left under the bell curve. So go ahead and, if you have your charts, look up a z-score of 1.1 to get the left area. .8643. and then go ahead and look up a z-score of 0.9.
.8159.
Okay? So those are the two left areas, and to find this area between those two values, we're gonna subtract those two left areas from each other. So subtract 0.8643 minus 0.8159. So this is the answer, 0.0484. This is the second way that we got this answer, and notice it's the same answer as the first way, or very close. So we say that this approach is an approximation. We're fitting a bell curve onto the original distribution. So this bell curve that we're fitting is normal, so it's a normal approximation to the original binomial probability distribution. And by doing this, we'll get the same answer, or a very close approximate answer to the correct, the exact answer. Any questions so far? So this example shows that this approximation is a very good approximation, that you're getting the same answer, doing it both ways. Finding the exact answer using the binomial probability formula, or fitting a bell curve onto it, you'll get the same answer or approximately the same answer. So at this point you might be thinking, okay, that's all well and good that we're getting the same answer, but in this situation, it was a lot easier just to use this binomial probability formula, just stick the numbers in the formula and get the answer. It was a lot easier than doing it the second way. And you'd be right, in this case, that is a lot easier, but it turns out that there's a huge payoff to doing it this way, doing it the second way. So let's look at another example where we can see the payoff. So let's say I had asked you, what's the probability? We're still in the situation of we're flipping a fair coin 100 times, and we want to know what's the probability that we observe at least 55 heads out of 100 flips. If we flip the fair coin 100 times. So, logically speaking, what does it mean to be at least 55?
Minimal.
55 or greater?
Yeah, 55 or greater, 55 or more. So this means that if we want at least 55 heads, then we're going to get either 55 heads out of 100 flips, or 56 heads out of 100 flips, or 57, and so on, all the way up through possibly 100 heads out of 100 flips. So now we have a situation where we have probabilities with events drawn by or. Which rule is that?
Addition.
Yeah, that's addition rule. So what that means is to find this probability, that's the same as splitting it up into probabilities of separate events and then adding all those together. So this is the same as the probability of 55 heads out of 100 flips plus the probability of 56 heads out of 100 flips flips, plus the probability of 57 heads out of 100 flips, all the way up to 100. So this requires, well, and how do you find each of these individual probabilities? How do you find the first probability? Probability of 55 heads out of 100 flips.
100 choose 55.
Yeah, it uses binomial probability formula that we talked about. If you didn't have this concept of fitting a bell curve onto the binomial distribution, we would have to get this answer by using this binomial probability formula on each of these individual probabilities. So we'd have to use that long, cumbersome formula from 55 to 100, so 46 different times. So that can be done, but that's a lot of work, and you don't want to do that. So instead of using that binomial probability formula 46 times and then adding up all the results, what we do instead is we're going to fit a bell curve onto this underlying binomial probability distribution, and once we have a bell curve, to find any areas that to find any probabilities that we want, we find the relevant areas instead. So now, if we go from 55 heads, which now, because we're fitting a continuous distribution onto a discrete one, we're going to give each discrete data point an area of 0.5 in either direction. Your book calls that continuity correction. So continuity correction is, originally we have a discrete distribution. The black distribution are discrete points, and we're fitting a bell curve onto it and define areas of points in a bell curve. We have to have regions around those data points. So for each data point that was originally discrete, we have to correct for continuity and give it a region so that we can find the area. And so the region is now 0.5 in either direction. So the data point at 55 really has this region between 54.5 and 55.5. So that's just this data point. If we want 55 or more, that means we're going to include everything to the right of it. So this green is continuity correction for just the one data point of 55. But if we want 55 heads or more, then we're including all the areas to the right of that as well. So that's what it means to be 55 or more heads out of 100 flips. So now this problem is simply find the area to the right of where this leftmost edge is. So what would the leftmost edge be? Yeah, 54.5. So to get the answer to this complicated problem, all you have to do is fit this bell curve and find the area to the right of 54.5. And this reduces down to a vanilla bell curve problem. So let's do it together. So again, we want this total area in green to the right of this left edge of 54.5. So we're going to find the z-score of 54.5. That's going to be 54.5 minus the mean, which we said before was 50, and divided by the standard deviation, which we said before was 5. And that z-score will be 0.9. And the left area of a z-score of 0.9, we already looked that up before. That was the 0.8159. So that's the left area relative to this data point, but we want the total right area, which is in green. So the right area will be 1 minus 0.841. So what does this mean? This means that if you were to flip a fair coin 100 times, originally the question was asking for the probability that you'll observe at least 55 heads out of 100 flips. And it turns out that at least 55 heads means 55 all the way up to 100. You could find the answer by adding up all the probabilities, but we said that that's a lot of work and we don't have the time or patience to do that. And we don't care about the answer that much. So what we're gonna do instead is fit a bell curve onto the underlying distribution and then find the probabilities by finding the areas relevant in that bell curve. So in this case, the areas relevant are 55, using continuity correction, has a region of between it of 54.5 and 55.5. That's the continuity correction for just the data point of 55. But we want 55 or more, so that includes all the area to the right of that as well. And so this final area becomes the area to the right of 54.5. So finding the z-score and then look it up in the table to find the left area, we subtract from 1 to get the right area. And this tells us that 18.41% of the time, we're going to observe at least 55 heads if we flip a fair coin 100 times. Any questions?
If we get a question that has the at least 55, we keep the continuity correction of that half point, so 54.5. We're gonna assume that half point stays there, even if it's a less than question, versus the 55.
Okay, good question. So let me do some examples of variations of this a little bit. But in this case, to get at least 55 heads out of 100 flips, that happens about 18% of the time. And some of you might be wondering, well, that seems a little weird because 55 heads is so close to 50 that shouldn't you observe it closer to 50% of the time? Why are you observing only 18% of the times you're observing 55 heads or more? Like, does this percentage seem small?
No.
Smaller than it should be.
The reason why the percentage doesn't seem small is because it's this and this and this. So the probability of getting exactly that makes sense because you're looking for that specific average or that specific probability.
Okay, so let me maybe phrase the question differently. Maybe if I had asked what's the probability of getting at least 50 heads out of 100 flips, based on the picture, you know that 50 is around where the actual mean is. So if we want exactly 50 heads, then technically using continuity correction, 50 is really between 49.5 and 50.5. So that's the continuity correction for just 50 heads is this region between 49.5 and 50.5. And then if you find the total area to the right of that, you're gonna get what answer? Approximately. So basically you're talking about
You're gonna get a little over 50%.
a little over 50%. So if you want the probability of exactly 50 heads out of 100 flips, it'll be a little over 50%. But this number 55 here seems pretty close to 50 heads, and so why are we getting an answer that's so distant from 50?
It's a standard deviation away.
Okay, very good. So it's an entire standard deviation away. So 5 heads might not seem like a lot, but measured in standard deviations, it is a lot. So what that's saying is that most of the observations are going to be between 55 heads and 45 heads. So this will be the bulk of the number of heads that you'll end up observing if you flip a fair coin 100 times. You'll see most of the time between 45 and 55 heads for a fair coin. But we want 55 heads or more, so you're excluding a lot of the bulk observations that you actually end up observing. So that's why we only end up seeing 18% of the time. Any questions? Okay, so let me address the question that was just asked. So in the previous example, we did the probability of at least 55 heads. So in that case, in the picture, we located where 55 was, but we said because of continuity correction, where this discrete point now becomes a region so that we can find the area and probability for that point. I'm going to make this region dramatically large so you can see it. So around 55, we're going to add and subtract 0.5. So the data point of 55 is really 54.5 to 55.5. So that's just the data point of 55. So this area here, if we were to find just this area, would be the probability of x being exactly equal to 55. So 55 heads. Now, if we want the probability of 55 heads or more, then we're going to include this entire region that represents just 55 and everything to the right of it as well to be more than that. So this will represent the probability of x is at least 55. So 55 or more. So, okay. So at least. So what if we wanted the probability of at most 55? So logically speaking, what does at most a number mean?
It's that or less.
Okay, good. So it could include the number or it could be less than that number. So at most 55 really means the probability of x is less than or equal to the number. So if you look visually at what that represents, we're including the number, in this case 55, and that number is actually represented by a region using continuity correction. So this number 55, again, is actually this entire region. But we want everything, including that region, as well as everything less than or to the left of that region. So that would include this as well. So if we wanted to find the probability that x is at most 55, then that would be this red region. So what if we wanted the probability that x is strictly less than 55? Let me do another picture. So 55 is going to be here. And then there's going to be this region around it, 54.5 to 55.5. So this region is that one data point at 55 itself, but we want it to be strictly less than that data point, so we want everything the left of that region that represents that data point. So left of this region would be only this part. So if you're going to be strictly less than the data point, we're not including that data point that is actually this region, so it's strictly everything only to the left. So this would be if we want the probability of the variable being strictly less than 1. And so in this case, since we're trying to find this area, then when we calculate the z-score, we use 54.5 as the data point for the z-score. And just as a review, if we wanted this probability of at most 55, that means we want to include the data point at 55 as well as everything to the left. So that would be this entire region, include the data point at 55, as well as everything to the left. So this total red area, so when we calculate the z-score and find the left area, then what is the rightmost boundary we're trying to find that area of? So it's this boundary, and what's the value we use for the z-score? It would be 55.5. Yeah. So in this case, the z-score calculation will be using 55.5. In the previous case, if we want strictly less than 55, we're going to use this boundary, which is 54.5. Okay, any questions? Okay, very good. So let's use another example. All right, so let's say that we take a 32 question multiple choice test. Four choices per question. And let's say that you randomly guess on all 32 questions. Let's say that passing means that you have to get at least 20 questions right. So the question is, what's the probability you'll pass if you guess on all 32 questions? So passing means that you have to get either 20 questions correct, or 21, or 22, all the way up to possibly 32. So passing is either you get 20 correct out of 32, or 21, or 22, and so on, all the way up through 32. So probability with or is which rule?
Addition.
Additional rule. So you could find this probability by taking the probability of 20 correct out of 32 and adding it to probability of 21 correct out of 32, all the way up through probability of all 32 correct out of 32. So how would you find each of these separate probabilities?
Binomial formula.
Yeah, binomial probability formula. So you would apply the binomial probability formula from 20 to 32, so 13 times, and then you would add up all the results, and you would get the correct answer, you'd get the exact answer. And that's fine, but that's gonna take a lot of work. Applying the formula 13 times and adding up all the results. So alternatively, what can we do instead? We can fit a bell curve onto this underlying binomial probability distribution. We know it's binomial because all of these probabilities fit the structure of a probability of this number of successes out of another number of trials. So all these probabilities are binomial, so the entire distribution will be a binomial probability distribution. So because we realize that, then what's the mean of this binomial probability distribution? It'll be that simple formula we talked about,
N times P.
which is n times p. So in this case, what's n, what's p?
N is 32 and P is 0.25.
Okay, very good. So if you're ever not sure what n and what p is, look at any one of these binomial probabilities. And remember, each binomial probability is in the structure of a probability of a number x of successes out of another number of trials, out of n trials. So n in this case is going to be 32. And then p is the probability of success per trial, and we've defined success here as being correct. So we want the probability of getting a question correct. So that's going to be 1 out of 4. So in this case, 32 times 1/4 is going to be 8. So that's the mean, and that makes sense because it's saying if you guess on all 32 questions, if a lot of people do that, then the average of all their scores is going to be 8, correct? And the standard deviation is going to fit that simple formula of the square root of NPQ, which is the square root of 32 times 1/4 times Q, which is the complement of P, or 1 minus P, which is 3/4. So you punch this in, what do you get?
2.45.
2.45, good. So what we're gonna do is, instead of adding up all these binomial probabilities, we're gonna fit a bell curve instead. So imagine having a bell curve, and then we want the probability of 20 correct or more. So we're going to locate where 20 is in this bell curve. And then we're going to use continuity correction because this original distribution actually wasn't a bell curve. We're only approximating a bell curve onto an actual discrete distribution. So we'll have to use continuity correction. So this discrete data point of 20 is now assigned an area of 0.5 in either direction. So this region represents just the one data point of 20. But we want 20 or more, so we're going to find the total area to the right of that data point as well. And so all the shaded area collectively has an edge that starts where?
19.5.
So we want this right area, but the edge of that right area is 19.5. So that's the value we're going to use in the z-score calculation. So So we're gonna calculate the area of 19.5. So the z-score will be the data point 19.5 minus the mean, which is 8, divided by the standard deviation, which is 2.45. So what's that z-score?
4.69.
4.69. And then we know that we can use the z-score table to locate the z-score to find the area to the left of that z-score. So in this picture, this z-score here ends up being 4.69. But this is actually not drawn to scale. Let me draw it closer to scale. So the data point having a z-score of 4.69 means that it's 4.69 standard deviations away from the mean. So the mean is where this peak is. So starting there at the center, we're going to move 4.69 standard deviations to the right. So that's actually very far to the right here. And we're essentially trying to find, because we want the probability of passing, which is 20 correct or more, we want a right area. So ultimately, we're going to find this right area here of a z-score of 4.69. And we've done something similar before, which is if you go to the z-score chart, you'll see that you won't be able to look at the z-score because the chart maxes out at a z-score of 3.5. So let's say that 3.5 is here. So this is not to scale either, but you can, it makes it dramatic that 4.69 is such a big z-score. So let's say 3.5 is here. So at a z-score of 3.5, using your chart, you know the area to the left is 99.99%. Therefore, the area to the right of that z-score will be 0.01%. But our z-score is even further to the right than the highest z-score in the book. So therefore, our z-score will have an area to the right of it that's greater than or less than 0.01%.
Less than.
Okay, good. So this z-score, the right area that we want, will definitely have a right area that is less than 0.01%. So therefore, the probability of passing on this multiple choice test will be less than 0.01%. Any questions? Okay, and so the point is, if you find yourself adding up multiple binomial probabilities, then instead of doing that, there's a shortcut. And the shortcut is fitting a bell curve onto the original binomial probability distribution and finding relevant areas instead. And in the process of finding the areas, you'll have to use continuity correction to give each data point a region so that you can find the area of that region representing the probability of that data point. Okay, any questions? All right, so the last thing I want to talk about related to this is we said that anytime you find yourself adding up multiple binomial probabilities, then think about using the shortcut and fitting a bell curve onto it instead. It turns out that just like with anything we talk about in this class, there's certain assumptions that have to be true for you to be able to do this with accuracy. So let's talk about what assumption has to be true. So we said that most of the time, a binomial distribution looks like this. And because of that, most of the time, we can fit a bell curve onto it. But let me use this absurd example. Let's say that we have a coin, and in this case, the coin's not fair. But the coin is so unfair that there are two heads on both sides of the coin. So there's a head on each side of the coin. So it's a two-headed coin. In that case, I don't know why we bothered flipping it, but let's say that we flip this coin 10 times, So flip a two-headed coin 10 times. And so if we're keeping track of the number of heads that we observe out of the 10 flips, then what do you think the distribution will look like?
It'd be a horizontal line.
Okay, you're on the right track. So maybe definitely not a bell curve, and definitely it can't be approximated with a bell curve. But let's work up to that. So first of all, what are all the possible values for the number of heads out of 10 flips?
10.
0 through 10, right? So anywhere between 0 through 10. Well, in the general case, 0 through 10. But in this case, for a two-headed coin, you can only observe 10 heads out of 10 flips. So at 10, you have maximum probability. So you have 100% probability of observing 10 heads out of the 10 flips. And all these other values that would normally be possible for any other coin are not possible. So you have 0 probability for each of these. So this is what the probability distribution looks like, is it's just one vertical spike at one value. So normally, a binomial probability distribution would normally look like this. And that's why you can fit a bell curve around it. But in this case, you can't fit a bell curve around this. Or you wouldn't get any accurate model fitting a bell curve to this. So because of that, there are assumptions that aims to quantify whether you're dealing with this situation or the general case. And typically, you're able to fit a bell curve if there's enough mass on both sides of the mean. In this case, there's not any mass on both sides of this mean. And so the way that we're going to quantify that is NP has to be at least 5 and NQ has to be at least 5. Those are the assumptions to be able to fit a bell curve onto the underlying binomial distribution. So notice that these two assumptions are joined with and, so that means that both have to be true. Okay, so in this example, the absurd example with the two-headed coin, let's go ahead and test these assumptions and see whether they're met. So what's N, what's P in that case?
N is 10 and P is 1.
Yeah, 1, good, 100% or 1. So P is gonna be 1, the probability of heads is 1. So N times P will be 10, and that's at least 5, so that's met. But let's try, but the second assumption also has to be met. So N is, here's 10, and then Q, or the probability of non-success, or tails, what's the probability of tails here?
0.
0, yeah. So 0 isn't at least 5, so there's not, this quantifies that there's not roughly the same amount of mass on both sides. And therefore, this assumption fails, and this tells you that to find any probability related to the situation, we're not able to fit a bell curve onto it. Any questions? So here, if you wanted to find the probability of 10 heads out of 10 flips, you would have to use the binomial probability formula. You couldn't rely on fitting a bell curve onto it. So let's look at the previous example, where we kind of just went ahead and fit a bell curve onto it. So really, you're supposed to check the assumptions first. So let's verify that this assumption was adequate so that we were able to correctly fit a bell curve and get the answer for that question. So
Number was 32, probability was 0.25.
yeah, N is 32. The probability of getting a question correct is 1 out of 4. So 32 times 1/4 is going to be 8, and then that's at least 5, so that's met. But we want to test the bottom assumption, N is 32. Q, the probability of getting a question wrong, is 3/4.
It's 25.
So that'll be 24. So both these assumptions are met because they're both at least 5. So because of that, we're correct and ended up fitting a bell curve under the problem. And we were able to get an accurate answer doing it that way because these assumptions were met. Any questions? So when you find yourself having to add up multiple binomial probabilities, you can either do that, or you can fit a bell curve onto the underlying binomial distribution as long as these assumptions are met. And then you'll get an accurate answer. So let me do one counterexample in the 3 minutes we have left. So let's say that we have 8 question multiple choice tests, or 8 question true false tests. And let's say you guess on all 8 questions and you want to know the probability that you'll get at least 4 correct, or let's say at least 5 correct out of 8. Let's say that getting 5 correct out of 8 is passing. So at least 5 correct out of 8 means that you either get 5 correct out of 8, or you get 6 correct out of 8, or 7, or 8. So probability joined by or is going to be addition rule, so this is the same as splitting this up into separate probabilities joined by addition. Plus probability of 6, plus 7, plus 8. So here, we're seeing that we need to add up multiple binomial probabilities to get our answer. And then we think, instead of adding up multiple binomial probabilities, we've been saying that we can fit a bell curve onto it as long as the assumptions are met. So are the assumptions met here for us to fit the bell curve? Okay, so let's try it. So the assumption again is NP and NQ have to be at least 5. What's N, what's P in this case?
N is 8 and P is 0.
Very good. Look at any arbitrary binomial probability. N is going to be the second number, which is going to be 8. And P will be the probability of success per question, and success is being defined here as getting a question correct. So that would be 1/4. Or no, not 1/4. But what is it?
1/2.
Yeah, 1/2, good, because it's a true false test. So each question can only be true or false, so there's 2 options. So getting a question right is 1 out of the 2 options. So 8 times 1/2 is 4, so already this assumption fails. And both of them have to be met, so really you don't even have to check the second assumption. But just for practice, let's check the second assumption. So N is going to be 8,
It's also 1/2.
also 1/2, because the probability of non-success or getting a question wrong is also 1/2. So this also fails. So this tells us that this assumption for a normal approximation to the binomial probability distribution is not met, and we're not able to fit a bell curve with accuracy. So in this case, because the assumptions aren't met, we're gonna have to add up these 4 binomial probabilities to get the accurate answer. And so on a test, be careful of that, is anytime you see multiple binomial probabilities, you're gonna wanna have the urge to fit a bell curve onto it instead. But before you do that, check the assumptions first. If the assumptions are met, then you can go ahead with the bell curve to find the probability. If the assumption is not met, then you'll have to add up the binomial probabilities manually. Any questions? Okay, that's it for today, guys. Have a good day.
Awesome. Tomorrow, I am trying, but I can't promise that I'm gonna be punctual tomorrow. All I see is nice Valley, they can kids going back and forth and getting them home before I can get here, so I get a little bit late. I did want to send an email on that one, because I haven't really got a lot of response to that one, but I'm just, hey, this is my next event. And that breaks it on, am I on the right track, taking it over?
For which part?
For this last problem?
Yeah, so each binomial probability, that's the first part of the formula. And then multiplied by, 1/2.
Would be the other side of this, is like 5 out of, like, that's the choice parts, and then multiply by the other side of it, I don't have, and.
Yeah, so that'll be this. So that'll be just this first binomial probability. And we'll do the same thing for the other three.
Well, I asked if I was on the right track, I just said, is that the answer?
Okay.
I knew that was the answer.
Yep, that is okay.